Most countries spend a decade debating infrastructure. China spent one building the world's largest bridge, the world's largest hydroelectric dam, the world's largest filled-aperture radio telescope, and one of the world's most ambitious next-generation particle accelerators. Those projects belong to completely different fields: transportation, energy, astronomy, fundamental physics, yet they emerged from the same national strategy. That should make us pause. Because countries rarely invest tens of billions of dollars in unrelated megaprojects at the same time, governments usually choose one priority, especially when economic growth begins to slow. China chose several. The interesting question isn't whether each project was impressive. The interesting question is why Beijing believed all of them were necessary. We'll come back to that. Most discussions about China's rise revolve around manufacturing exports, trade surpluses, or military modernization. Those are important, but they often overlook the physical foundations that make those developments possible. Factories require electricity. Supply chains require transportation. Scientific breakthroughs require research infrastructure that can take decades to build. None of those appear overnight. This story begins long before a single bridge cable was stretched across the sea. In 2011, China's 12th five-year plan expanded investment not only into industrial production, but also into strategic science, advanced transportation networks, clean energy, and frontier research. Different ministries handled different pieces. The Ministry of Transport accelerated national connectivity. The National Development and Reform Commission coordinated long-term infrastructure planning. Scientific institutions under the Chinese Academy of Sciences received increasing support for large-scale research facilities that many countries simply could not afford to build. Viewed separately, these looked like independent projects. Viewed together, they resemble something much larger. Take the Hong Kong, Zhuhai, Macao Bridge. Stretching roughly 55 kilometers, it became the world's longest sea-crossing bridge and tunnel system when it officially opened in 2018. Building across one of the busiest shipping lanes on Earth meant engineers could not simply connect two coastlines. Massive cargo vessels still had to pass through. Their solution was unusual: construct an underwater tunnel in the middle of the crossing while linking it with artificial islands created from reclaimed land. That decision alone required engineering methods developed specifically for this project. The bridge reduced travel time between Hong Kong and Zhuhai from several hours to around 45 minutes under normal conditions. For commuters, that meant convenience. For manufacturers, it meant something else entirely. Every minute removed from logistics reduces transportation costs across thousands of deliveries. Small savings repeated millions of times become national economic advantages. Infrastructure rarely makes headlines after opening. Its effects continue for decades. Then there is the Three Gorges Dam. Although the project itself began years earlier, the decade after its completion demonstrated why Beijing considered it indispensable. With an installed generating capacity exceeding 22,500 megawatts, it remains the world's largest hydroelectric power station. In productive years, it generates enough electricity to power tens of millions of households while reducing dependence on coal-fired generation. Critics have raised valid concerns regarding environmental impacts, population displacement, and ecosystem changes along the Yangtze River. Those concerns deserve attention because they are supported by substantial research. Yet Beijing evaluated the project through another lens as well: long-term energy security. Countries that cannot guarantee stable electricity struggle to sustain industrial growth. China had no intention of accepting that limitation. Here's an observation that is almost oddly simple. Steel mills do not care about political speeches. Semiconductor fabrication plants do not operate on optimism. Data centers cannot run on strategic ambitions alone. They require electricity every second of every day. Reliable energy becomes a national asset long before it becomes a political slogan. This is where many analyses stop. Mine doesn't, because transportation infrastructure and electricity explain only part of the picture. During the same period, China was quietly constructing facilities that had no immediate commercial return at all. One searched the universe for signals billions of light years away. Another aimed to answer questions about the smallest particles known to science. On paper, neither project increases quarterly GDP. In practice, they may shape technological leadership for decades. That raises a larger question. Why would a government simultaneously invest in bridges, dams, astronomy, and particle physics while much of the world focused on quarterly growth figures. At first glance, the connection seems weak. By the end of this story, I think it will look unavoidable. The easiest mistake to make is assuming these projects were symbols of national pride. They certainly became that. But symbols are expensive luxuries, and governments rarely spend tens of billions of dollars simply to impress the world. When you examine the planning documents, the funding structures, and the timing, a different picture begins to emerge. China wasn't collecting engineering trophies. It was building the foundations of a country that could operate with fewer strategic constraints. That distinction matters. Consider FAST, the 500-meter aperture spherical telescope in Guizhou province. Officially completed in 2016, FAST became the world's largest filled-aperture radio telescope, with a dish measuring 500 meters across. That's roughly the size of 30 football fields placed side by side. Most people hear radio telescope and immediately think about aliens. That's understandable. The reality is considerably more important. FAST listens for incredibly weak radio signals arriving from distant pulsars, galaxies, and mysterious cosmic events that remain poorly understood. Its sensitivity exceeds that of many earlier observatories, allowing Chinese scientists to detect astronomical phenomena that were previously impossible to observe. At first glance, this seems disconnected from economics. It isn't. Large scientific instruments rarely produce immediate profits. Instead, they produce people. Engineers learn to design ultra-sensitive receivers. Software teams develop algorithms capable of processing enormous quantities of information. Precision manufacturing companies learn to fabricate components that operate within microscopic tolerances. Universities gain experience running projects involving thousands of specialists. Knowledge spreads far beyond the original telescope. That pattern appears repeatedly throughout history. The United States didn't build the Apollo program because selling moon rocks was profitable. The technologies developed for space exploration later transformed computing, communications, and advanced manufacturing. Europe's particle physics laboratories helped advance medical imaging and semiconductor technologies. Basic research often appears economically inefficient until 20 years later. China clearly studied those examples. The Chinese Academy of Sciences didn't view FAST simply as an astronomy project. It became part of a broader national effort to strengthen scientific capability, attract international researchers, and reduce dependence on foreign research infrastructure. Scientific influence isn't measured only by published papers. It's measured by who owns the instruments everyone else wants access to. There's another layer. When countries host world-class research facilities, they become destinations for talent. Graduate students arrive, international collaborations form, domestic universities gain prestige, private technology companies establish relationships with research institutes. None of this happens overnight, but over a decade the effects compound. Talent follows opportunity, opportunity follows infrastructure. That sequence is surprisingly consistent across modern economic history. Then we arrive at perhaps the least discussed project of all, the high-energy photon source, and China's broader ambition to construct one of the world's most advanced particle accelerators. While Europe operates CERN's Large Hadron Collider, China has spent years planning facilities capable of pushing the frontier of particle physics even further, including proposals for the Circular Electron-Positron Collider, or CEPC. Notice something interesting. Governments rarely spend billions trying to answer questions about subatomic particles unless they believe those answers will eventually produce technologies nobody can predict today. Particle accelerators aren't simply machines for physicists. They drive innovation in superconducting magnets, cryogenic engineering, vacuum systems, radiation detection, medical imaging, advanced materials, and high-performance computing. These technologies eventually find their way into hospitals, aerospace industries, semiconductor manufacturing, and defense applications. The path isn't direct, but it exists. Western analysts sometimes argue that China is excellent at commercializing existing technology, but weaker at producing fundamental scientific breakthroughs. That's a serious argument and deserves consideration. Citation impact, Nobel Prizes, and frontier discoveries still favor the United States and Europe in many disciplines. Yet that comparison raises another question. Can a country realistically expect to dominate future scientific discoveries without first constructing the laboratories where those discoveries become possible? I'm not convinced. Buildings alone don't produce innovation. Brilliant people do. But brilliant people equipped with world-class instruments usually outperform equally brilliant people forced to wait in line for access somewhere else. That's the difference. There's also an economic dimension that receives surprisingly little attention. Megaprojects create industrial ecosystems. Constructing fast required precision steel manufacturing, advanced cable systems, specialized robotics, and highly accurate surveying technologies. Building particle research facilities demands domestic suppliers capable of producing components that previously had to be imported. Each project expands industrial capability. Each capability strengthens the next project. Eventually, the projects begin reinforcing one another. Think back to the bridge from part 1. Faster logistics help manufacturers. Reliable electricity powers factories. Scientific infrastructure develops advanced technologies. Those technologies improve manufacturing, which generates economic growth, which finances the next generation of infrastructure. It's less like building 4 separate landmarks. It's more like assembling gears inside a machine. Here's my opinion. Many countries evaluate infrastructure by asking whether a single project pays for itself. China appears to ask a different question. Does this project make the next 20 projects easier, faster, or cheaper? That's a fundamentally different investment philosophy, and whether one agrees with it or not, it deserves serious attention. The real test, however, isn't whether these projects are impressive. It's whether they actually change China's position in the global balance of science, technology, and industrial power. That's where the story becomes considerably more complicated. There quotes a tendency to measure national power using the headlines of the day: quarterly GDP, stock markets, election cycles, trade disputes. Those indicators matter, but they also create a very short time horizon. Infrastructure operates on a completely different clock. A bridge can shape trade for 50 years. A research laboratory can influence technology for an entire generation. That's why judging these projects by their immediate financial return misses the point. Let's return to the number from the beginning: 1 decade. Building the world's largest sea bridge, maintaining the world's largest hydroelectric dam, completing the world's largest filled-aperture radio telescope, and preparing for one of the world's most ambitious particle physics programs within roughly the same strategic period required something far more valuable than money. It required planning continuity. That is becoming increasingly rare. Whether people admire China's political system or criticize it, one reality is difficult to ignore. Beijing has demonstrated an unusual ability to pursue infrastructure plans that extend well beyond a single political cycle. 5-year plans don't guarantee success, but they create consistency. Ministries, provincial governments, state-owned enterprises, universities, and financial institutions often work toward the same long-term objectives. Consistency compounds. Many Western democracies possess stronger innovation ecosystems in areas like software, venture capital, and entrepreneurship. Silicon Valley remains unmatched in creating globally dominant technology companies. American universities continue to lead in many scientific disciplines. Europe's engineering tradition remains among the strongest in the world. Those strengths are real. But infrastructure tells a different story. The American Society of Civil Engineers has repeatedly graded much of the United States infrastructure below ideal standards, pointing to aging bridges, highways, water systems, and electrical grids requiring significant investment. Europe faces similar challenges in modernizing energy systems while balancing environmental regulations and fiscal constraints. China entered the 21st century with different priorities. Instead of asking whether it could afford to build, Beijing often asked whether it could afford not to. That distinction shaped thousands of decisions. Take high-speed rail as another example. Although it isn't the main subject of this discussion, China's network now exceeds 45,000 kilometers, by far the largest in the world. The same construction companies, engineering firms, steel manufacturers, and project management systems involved in rail expansion also contributed experience that benefited other megaprojects. Expertise transfers. Workers trained on one complex project become supervisors on the next. Companies that master precision engineering compete for increasingly sophisticated contracts. Universities adapt curricula to meet national demand. Before long, the country develops capabilities that cannot simply be purchased from abroad. This is where the conversation becomes more nuanced. Critics often argue that some Chinese infrastructure projects suffer from overcapacity. There are examples supporting that claim. Certain regional airports operate below expected passenger levels. Some local governments accumulated heavy debt financing ambitious construction. Not every investment generated the projected economic return. Those criticisms shouldn't be dismissed. They're supported by evidence. Yet focusing exclusively on underused projects risks overlooking the broader strategic outcome. The question isn't whether every bridge, railway, or laboratory became an immediate success. The question is whether, taken together, they expanded China's industrial, scientific, and engineering capacity. The data suggests they did. China now produces more engineers each year than almost any other country. It leads global manufacturing output, accounts for a significant share of scientific publications, and has become increasingly competitive in advanced technologies ranging from renewable energy to quantum communications and artificial intelligence. Of course, correlation isn't causation. These achievements weren't produced solely by megaprojects. Education reform mattered. Industrial policy mattered. Global trade mattered. Foreign investment played an important role during earlier decades. Private companies such as Huawei, BYD, and DJI accelerated technological development in ways government planners alone could never have achieved. Reality is rarely simple. Still, it's difficult to ignore how frequently physical infrastructure appears beneath these successes. Factories require electricity generated by massive power systems. Research depends on laboratories built years before discoveries occur. Advanced manufacturing relies on transportation networks capable of moving components quickly across enormous distances. The foundations usually become invisible once they're finished. That's precisely what makes them powerful. Here's the reversal I think many observers miss. For years, analysts described China's infrastructure boom primarily as an economic growth strategy. Increasingly, it looks like something broader. These bridges, dams, research facilities, and laboratories weren't simply designed to increase GDP. They were designed to reduce dependence. Dependence on imported energy, dependence on foreign technology, dependence on overseas scientific infrastructure, dependence on logistical bottlenecks beyond China's control. Whether that objective succeeds completely remains uncertain. But once you view these projects through the lens of strategic resilience rather than immediate profit, many decisions that previously seemed excessive begin to look surprisingly coherent. I'm still left with one question. If the first phase was building the physical foundations, what exactly is China preparing to build on top of them over the next 20 years? Because I don't think these megaprojects were ever intended to be the final destination. I think they were only the beginning. Let quotes go back to the contradiction that opened this video. Most countries spend years arguing about what to build first. China spent roughly the same decade constructing infrastructure that touched transportation, energy, astronomy, and frontier physics simultaneously. At first, those looked like four separate stories. By now, I hope they look like one. Because none of these projects exists in isolation. The Hong Kong, Zhuhai, Macao Bridge shortened logistics across one of China's most economically productive regions. The Three Gorges Dam strengthened the country's electricity supply while supporting an industrial economy that consumes more power than any nation in history. FAST gave Chinese scientists a research instrument that attracts international collaboration instead of depending entirely on facilities overseas. And China's continuing investment in next-generation particle physics signals that Beijing intends to compete not only in manufacturing existing technologies, but also in discovering entirely new ones. Different projects, one direction. There's another point that deserves attention. Infrastructure changes how a country thinks. When governments repeatedly complete projects that many experts initially considered unrealistic, confidence grows, not only among political leaders, but among engineers, universities, construction firms, investors, and young students deciding what careers to pursue. Success creates expectations. Expectations influence ambition. That may be one of the least measurable but most important outcomes of all. History offers similar examples. The United States transformed itself during the 20th century through projects such as the Interstate Highway System, Hoover Dam, the Apollo program, and later the Internet, which originated through publicly funded research before becoming a global commercial platform. Japan's Shinkansen wasn't simply about trains. It demonstrated precision engineering to the world. Europe's CERN became a symbol of scientific cooperation, while contributing technologies that extended well beyond particle physics. China appears to be following the same historical pattern, but at a different scale and speed. That doesn't mean every investment will succeed. Far from it. China faces serious structural challenges that cannot be ignored. Local government debt remains significant after years of infrastructure-driven growth. Demographic trends point toward a shrinking working-age population. The property sector has experienced prolonged stress. Trade tensions with the United States and several Western economies continue to reshape global supply chains. Advanced semiconductor restrictions have also complicated Beijing's technological ambitions. These are not small obstacles. They could slow future progress considerably. But slowing progress is not the same as stopping it. One mistake I think analysts sometimes make is assuming that if China's economy grows more slowly than before, its strategic projects automatically become irrelevant. Those are two different questions. A country can experience weaker growth while continuing to strengthen its scientific capabilities. Likewise, a rapidly growing economy can still neglect long-term infrastructure. Growth rates tell only part of the story. Capacity tells another. Here's my opinion. The real competition between major powers over the next 20 years will probably not be decided by a single technology, a single election, or a single military system. It will be decided by which countries build ecosystems capable of producing new industries again and again. Bridges move goods, power plants sustain factories, research facilities generate knowledge, universities train people, industries commercialize discoveries. When those pieces reinforce one another, national strength becomes much harder to disrupt. That doesn't mean China has already won. I don't believe that conclusion is supported by the evidence. The United States still possesses extraordinary advantages in higher education, financial markets, venture capital, software innovation, aerospace, biotechnology, and many areas of frontier research. American allies collectively represent enormous technological and economic capacity. Competition remains very much alive, but competition has changed. It is becoming less about isolated inventions and more about the systems capable of producing inventions continuously. That brings us back to the question we left unanswered. Why did China invest in a bridge, a dam, a radio telescope, and a particle accelerator during roughly the same decade? Because Beijing appears to view infrastructure the way many companies view operating systems. You don't notice it every day. It doesn't generate headlines every morning, but everything else depends on it working. Whether that strategy ultimately succeeds will take decades to judge. My prediction is this. Over the next 15 to 20 years, the countries that consistently invest in long-term scientific and physical infrastructure, even when the returns seem distant, will hold a decisive advantage in emerging industries like artificial intelligence, quantum technology, advanced energy, robotics, and space exploration. The winners won't simply invent more. They'll build the environments where invention becomes routine. One final thought. When historians look back at the early 21st century, they may not remember every speech delivered by world leaders. They may remember the bridges that redirected trade, the dams that powered factories, the telescopes that expanded scientific knowledge, and the laboratories that quietly shaped technologies the rest of us hadn't imagined yet. Sometimes the biggest story isn't who spoke the loudest, it's who kept building.